Hello all, today we'll be reviewing the first question from Midterm 1, Spring 2014, which deals with Python programming. In a recent lab, you studied the motion of an object falling under the force of gravity and air resistance. Your friend has asked you to help her with a similar experiment that involves testing a model for the motion of a pelican as it dives below the surface of the ocean. From direct observation, she notes that the pelican enters the water with a speed of 15 meters per second and at an angle of 20 degrees from a vertical line drawn perpendicular to the surface of the water as indicated by the diagram. Current pelican theory predicts that as they dive through the water, they experience a drag force proportional to their speed cubed. The code listed on the next page, which is nearly identical to your computer model from the lab, is missing a few lines of code. In the space provided, add the statements necessary to predict the motion of the pelican. Okay, so we're going to go through the how to approach this problem, how to approach the Python programming behind this problem, and how we can relate that back to the physics concepts from class. Okay, so the first line I want you to write in is the pelican's velocity, which is denoted as pelican.vel. And here's actually where I lost the most points because I didn't actually note it the right way. First of all, before we even note the pelican's velocity, we should go back to the diagram. And we can see that the pelican's velocity can be split up into its x and y components. So if it's diving in this way, you say that it has an x component this way and a y component this way. And in order to note this, we just use trigonometry. So if this is the magnitude, VI, which we say is 15 meters per second, then you know that the x component is 15 sine 20. This is 20 degrees. Sine 20 is the x component, and then negative 15 cosine 20 is the y component. But the way that you denote it, and the reason I got points off, is you have to make sure that it's in vector formatting. So you put vector 15 sine 20 negative 15 cosine 20, and remember that, and so this is how you're supposed to note it. Remember that when you're putting vector form, it's always vector x, vector shouldn't be capitalized, x, y, z. And so in the x direction it's moving 15 sine 20, and the y direction is moving negative 15 cosine 20, and the z direction it's not moving at all because it's not 3D, so it's just going to be 0. So this is one of those instances where just because it's the x coordinate doesn't mean it has to be cosine, and just because it's the y coordinate doesn't mean it has to be sine. So essentially you just have to keep in mind this diagram. Okay, so that said, the bulk of your points actually come from the next section, which is creating the while loop. And so then the net force that's going to be on the pelican is going to be the force of air resistance, and the force of the weight. So let's identify those first before we write out the net force. Okay, so make sure that they're in vector format. So your force of the earth, let's say F earth, equals the vector, make sure it's in vector format, 0, negative g being what we already see right here is the gravitational acceleration on Earth, multiplied by the mass of the pelican, and this is what essentially gives you the weight, 0. And you know that the weight is only moving in the y direction, so that's why the x and z components are going to be 0 in this case. Okay. And then moving forth with that, one moment. We have the force of the air. And the force of the air, again, vector, it's going to equal, no, actually force of air is not vector, I'm sorry about that. Force of air is not vector, it's a scalar. It's going to be equal to the to the proportionality constant, which we denoted as negative b, multiplied by the pelican's velocity. And because we denoted the force of the air is going to be denoted as v cubed, the drag force proportionality constant multiplied by the speed cubed. We already multiplied by the speed's velocity, its vector, once. So next time you have to do it, you have to multiply by its magnitude because you can't multiply two vectors together, or two velocities together for that instance. So magnitude 2 of pelican.val. And then you have to add these net forces together. So the force of the earth, which is essentially the force of the weight acting on the pelican, and the force of the air, which is the air resistance. You add them together, so the force of earth plus F of air And once you have the net force, you can actually use that to identify the velocity of the pelican is going to be going in. So you know the velocity final is equal to, okay, this cannot be capitalized. Velocity final is equal to velocity initial multiplied by the net force divided by the mass of the pelican. And then all of this multiplied by the change in time, which is denoted as delta t. And this is something that you can derive using Newton's fundamental law of F equals, well, or change of momentum is equal to net force multiplied by change of time. And then you can update the pelican's position by saying that pelican.pause, which is what we're going to use to denote pelican's position, is equal, the final position is equal to the initial position multiplied by the final velocity multiplied by delta t. Also here, this should be, so make sure you use an asterisk when you're denoting it. Okay. And that's pretty much it for the code. A lot of it is just the conventions, things to keep in mind. But yeah, so never forget like the negative in front of the proportionality constant. I got to point out for that. Remember, you cannot multiply two velocities together because you can't multiply two vectors together like that. So in this case, you're going to have to multiply after the velocity the magnitude. And yeah, that's pretty much it. Okay, hope this helps and good luck.